Hello, is my voice coming?
Yes, you're audible.
Nisha, can you just check if you are able to share the screen?
Yeah, okay.
Yeah, fine.
Yes, okay.
Are Janvi and Vihang joining too?
Vihan's joining. Janvi, I don't think so.
Okay.
We'll be starting in 5 minutes.
I think we can start now.
All right. So, hi, welcome to your second Learner Space Meet. Today we'll be covering coordinate systems and time. I'll begin right now. So, yeah, I'll start with coordinate systems. So, the first question that arises is why use coordinate system for things in space? So, let's look at some examples to answer this. So basically, say you want to find the distance of a star from the Earth. So for that, you need to observe the star over some time. So for that, you need to know its specific location in the sky. Similarly, if you want to observe a star or a planet from Earth, you need to know its exact location in the sky. So, a lot of research in astronomy involves pinpointing things in the sky. For that, coordinate systems they provide a metric for that or a standard for that. So, now that we have established why we need a coordinate system, let's figure out how to uh, figure one out. So, basically, let's look at the Earth. How do we pinpoint a location on the Earth? We use the geographical coordinate system. So, to pinpoint a location, you need its latitude and its longitude. So, the latitude is basically the angular distance of the location from the Earth's equatorial plane. Similarly, longitude is the angular distance of the location from the Greenwich meridian. So all of the coordinate systems that we discussed today, they have a similar system. So one coordinate will be the angular distance of the celestial body from a reference plane, and the other coordinate will be the angular distance of the celestial body from a fixed direction. Now, in the case of Earth, this is very convenient because Earth is a sphere and all locations they lie on the surface of the sphere. The universe isn't a sphere. So how do we define something like this for space? So for that, we define a sphere known as the celestial sphere. So the celestial sphere is an abstract sphere which is concentric to the Earth. So basically, all celestial objects they lie on the sphere. Now, this doesn't make much sense because, say, the sun and the pole star they lie at different distances from the Earth. So how can we claim that both of them lie on the sphere? That will be claiming that they're equidistant to the Earth. So so basically, the coordinates that we define on the basis of the celestial sphere, all of them are angle-based coordinates. They're not distance-based coordinates. And as we know, angles are independent of distance. So basically, the celestial sphere, it's just that we define that these objects that they appear to lie on the sphere. So it's not that they do, we just assume that they do, and it doesn't cause a problem in assuming the coordinate. So there's like a few properties that the sphere has. So the circle where the Earth's equatorial plane intersects the celestial sphere, that is known as the celestial equator. Similarly, the points where Earth's rotational axis intersects the celestial sphere, those are known as the North Celestial Pole and the South Celestial Pole. Now, I'll be playing this small clip which to help you guys understand the gist of a celestial sphere. So yeah, wait. Oh,
But this is when the sun is at its highest position above the horizon. It is transiting the meridian, so it's at its greatest altitude. And I'm saying it's at its highest or highest altitude because as the day continues, the sun now begins to decrease its altitude as it moves toward the southwestern sky, gradually moving toward the due west and setting even just a little bit due north. This simulation is being run in August, so we're getting a good idea of what's going on tonight. Well, the sun sets and the stars come out. And the thing to notice here is that we have the stars doing the exact same thing that the sun appears to do. They rise in the east, they cross over the meridian, they transit the meridian, and then they set toward the west. And the thing is that this pattern will repeat itself. So as these stars continue to set very gradually over time, the sun will begin to rise once again. And now it's daytime. So a new day dawns, the pattern repeats. And it's for this reason that many ancient civilizations, and indeed certainly many ancient Greek astronomers, felt that the stars must be some kind of a vast sphere and not a dome at all. So we have the sphere that seems to be rotating around us, and with this regular predictive cadence, they assumed that this must mean that the stars are imprinted upon a sphere. Well,
yeah, so there's a lot happening in this clip. So first of all, this circle isn't a sphere. So it's imagine that you lay on the grass and you're looking towards the sky, and your peripheral vision covers 360 degrees. So this is the view you would be seeing. Now, what is this grass? So we define the horizon. So the horizon is a plane that passes through the observer, and it is also tangent to the earth. So the grass in this clip is basically the horizon. And now imagine a vertical line which is perpendicular to the horizon and passes through the observer. The points where this line intersects the celestial sphere, these points are known as zenith and nadir. So basically, zenith is the point on the celestial sphere which is directly above the observer. Nadir is directly below the observer. So if you can see in this video, you see the Z in the middle of the circle, right? So that's the zenith. Now we also observe this line in the middle. So this isn't exactly a line. This is a circle known as the local meridian. So local meridian is basically a circle that passes to the north celestial pole and the zenith, which is also perpendicular to the horizon. And the points where it intersects the horizon, they are known as N and S. So you see the N at the end of the circle, right? At the end of the local meridian in red. So yeah, those are the points where the local meridian intersects the horizon. So when a star crosses the local meridian, like how we saw in the video, the sun crosses the local meridian, we call that culmination. And yeah, so now that we have these details written, let's move on to our first coordinate system. So our first coordinate system is the horizontal coordinate system. So like I said, all of these, they have a reference plane and a fixed direction. In this case, the reference plane is the horizon and the fixed direction is the local meridian. So as you can see, the horizontal coordinate system is from the observer's point of view. So the first coordinate is the angular distance of a celestial object from the horizon, and angular distance of object from the horizon. It's known as the altitude. The second coordinate is known as the azimuth, and it's the angular distance of the object from the local meridian. So more specifically, it's the angle measured from N, measured clockwise from N, and yeah, its range is 0 to 360 degrees. This system isn't exactly uniform. You cannot use this as a metric, because if somebody in Delhi and somebody in Mumbai, they're observing the same star, they will note down different coordinates, although they're observing the same star, because this system depends on the position of the observer and the time. So you cannot use this in star catalogs. So do we have a system which is independent of the observer's position? Yes, we do. So our second coordinate system is the equatorial coordinate system. So in this system, the reference plane is the equatorial plane, how we defined it before, and the fixed direction is the vernal equinox. Well, what is the vernal equinox? So to understand the vernal equinox, we need to understand the ecliptic. So the path the sun traces on the celestial sphere over the course of a year is known as the ecliptic. So this is kind of like a figure on the celestial sphere, and the ecliptic, it intersects the celestial equator at 2 points. These points are known as the equinoxes. Now, vernal equinox is the point where the sun goes from the southern hemisphere to the northern hemisphere. So vernal equinox typically occurs around March 21st, and March 21st, that's why the symbol is also a ram. So vernal equinox is basically a point that lies on the celestial equator and the ecliptic as well. So this is the reference direction. So our coordinates for this system are the declination, which is the angular distance of the star from the equatorial plane, and the right ascension, which is the angular distance of the star from the vernal equinox. More specifically, it's measured anti-clockwise along the equator. Now, what's special about right ascension is it's measured in the units of time. Well, how does that make sense? So basically, the Earth rotates 360 degrees in 24 hours. So in an hour, it rotates 15 degrees. So if you know the angle the Earth rotates by, you can find how much it rotated in terms of time units. So speaking of time units, we also define something known as the hour angle. So hour angle is something specific to the observer. So it's the angle that a celestial object makes with the local meridian when measured clockwise, and it is expressed in terms of time units. The hour angle of the vernal equinox is called the sidereal time. So any questions so far? Okay, I'm assuming none, so I'll be moving on. So our next coordinate system is the ecliptic coordinate system. So this coordinate system is very useful for
Anisha,
calculation. Yes.
Yuvraj has a question. He has raised a hand.
Oh, Yuvraj, you have a question?
Yes. Can you explain the local meridian once again, please?
Okay. So basically, local meridian is a circle on the celestial sphere which passes to the zenith and the north celestial pole. And this intersects the horizon perpendicularly, right? Any other doubts? Any specific doubts?
Actually, the name was local meridian, so I thought it was also observer dependent.
Yes, it is observer dependent. Because the zenith is observer dependent, right?
Okay, take.
So zenith is the point on the celestial sphere directly above the observer. So your zenith varies from like if an observer is in America, their zenith varies from your zenith. So because of that, the local meridian will also change. And it's also perpendicular to the horizon. So it's not a constant thing, it's observer dependent. So our NNS, so is the horizon. All of this depends on the observer, which is why the horizontal coordinate system cannot be used as a standard. So is it clear?
Yeah, it is. Thanks.
Okay. Yeah, okay. So yeah, ecliptic coordinate system is mainly used for objects in the solar system. It's very useful for defining and research on the solar system. So basically, the reference plane in this case is the ecliptic, and the fixed direction is and the fixed direction is the vernal equinox. So if you would have noticed, the fixed direction in the equatorial system was the vernal equinox as well. But so the first coordinate in this system is known as the ecliptic latitude, which is the angular distance of the celestial body from the ecliptic. The second coordinate is the ecliptic longitude, which is the angular distance of the star from the vernal equinox, and it is measured anti-clockwise from the ecliptic. Now, like I said, the fixed direction is identical in the equatorial coordinate system and the ecliptic coordinate system. It does not mean that the second coordinate in both these systems are identical because they're measured along different planes. So, like I said, it's used for objects in the solar system. So you can also define the system to be heliocentric, which is centered at the sun. You can define it to be geocentric, like we just discussed, and you can also define it to be topocentric, which is observer centric. So yeah, it's very convenient. So like we defined a system for objects in the solar system, we also have one for research on the Milky Way. So this is known as the galactic coordinate system. So for studies of the Milky Way galaxy, this is very convenient. So in this case, the reference plane is the plane of the Milky Way itself, and the fixed direction is the line joining the sun and the galaxy center. So in all of the coordinate systems we've discussed so far, it's either the Earth at the center of it's either Earth centered or the observer centered. But in this case, the sun is at the origin of the coordinate system. So there might be a question that if the sun is at the origin, can we still assume the celestial sphere to be applicable? Because, like I said, celestial sphere is defined on around celestial sphere is defined to have Earth at its center? The answer is yes, because in the galactic scale, the distance between the Sun and the Earth is very small. So you can take them to approximately coincide. So you can assume both of them are at the center. So the first coordinate in this system is the galactic latitude, which is the angular separation of the celestial object from the galactic equator. I mean, the plane of Milky Way. And the second coordinate is the galactic longitude, which is the angular separation from the line joining the center of the galaxy and the sun. And this is measured along the galactic equator. So yeah, that's all I had for coordinate systems. Please feel free to ask any questions. All right, so I'll take that to I'll take that and move on. So I'll be handing it over to Jatin to cover time.
Yeah, sure. Firstly, if anyone has any questions to Anisha, then they can raise their hand and I'll allow them to speak. No questions?
Yeah,
Yes, Yuvraj has a
Yuvraj.
question.
Yes. Can you go back to the galactic system? Because I could not really understand how you said there were angles in the plane of Milky Way.
Okay. Yeah. So basically, we define our origin to be the sun, and one reason for that is sun lies very close to the plane of the Milky Way. So basically, and the specific direction, it's the line joining the center of the Milky Way and the sun. So as the sun lies very close to the plane, they kind of form a line which also lies in the plane. So you have any specific doubt?
Mainly the galactic latitude B, as it's written, that is
Hmm.
the angular separation of a star from the galactic plane, positive
Yes.
northwards and negative southwards.
Yes.
So we are not taking the Milky Way as a simple flat plane, right? So we are just taking it as a 3D surface, like 3D plane here. There can be
Oh, okay.
stars above the sun and stars below the sun.
Oh, okay. Yeah, you're right. Okay, so basically you can define it to be the okay, so in terms of the celestial sphere, you can kind of define it to be a circle which with sun at the center and it passes to the galactic equator. So a great circle is basically a diametric circle on the sphere. So it's basically a great circle passing to the galactic center. So yeah, you were right about the plane thing, but yeah, you can define it to be a specific plane which passes to the sun and the center of the galaxy. And yeah, you can define the stars in the Milky Way to be either above that or below that.
Thank you.
Yeah, okay. Any other questions? All right, I'll hand it over to Jatin.
Yeah, thanks, Anisha. That was a really nice presentation. Now let's move on to the part 2 of our presentation. That's tracking time in the sky. First off, let's recap a few terms that will be needed later on. First is the vernal equinox, the point where the sun crosses the celestial equator moving northward. That's approximately March 21, and it is also the 0 point for the right ascension. The right ascension is the angular distance of a star eastward from the vernal equinox, measured along the celestial equator. And the R angle, denoted by H, is the angular distance of a star westward from the local meridian. This is zero at culmination and it grows as Earth rotates. Both the right ascension and the R angle are measured in the time units and not angle units. The sidereal time is the R angle of the vernal equinox. Sidereal time is denoted by theta. It is the theta is equal to H plus A. Sidereal time tells you how far the sky has rotated since vernal equinox last crossed your meridian. The rotation it denotes the rotation of the sky since the vernal equinox has last crossed your meridian. So the question is a day really 24 hours? What is the time taken by Earth to complete one full rotation? Now, rotation is a relative term. It depends on the reference from which we are seeing. In reference of the sun, the duration is 24 hours. But in reference of a distant star, will the duration be same? The spoiler is they're not actually the same. By the time Earth reaches from point A to point B, as we can see sorry, as we can see in this figure, by the time the Earth reaches from point A to point B, Earth has to complete one rotation. Along with that, Earth has to rotate approximately 1 degree more to complete one rotation with respect to the Sun due to the revolution of the Earth. And that extra 1 degree requires approximately 3 minutes and 53 seconds. So for Sun, the whole solar day is 24 hours. But with respect to a distant star, a sidereal day is 23 hours, 56 minutes, and 4 seconds long. And that 1 degree contributes the other 3 minutes, 56 seconds part. So sidereal day is equal to 23 hours, 56 minutes, 4 seconds. And one solar day is 24 hours, 0 minutes, 0 seconds. And the difference is 3 minutes and 56 seconds. In one full year, this 3 minutes and 56 seconds add up to one whole extra sidereal day. This means that every night the stars rise 4 minutes earlier than the night before. And in 6 months, a star that was visible at midnight is now visible at noon, which means basically invisible. Now let's look at the maths. Let us assume the orbital period of a planet is P, its sidereal day is tau star, and the solar day is tau. Then for a prograde spin, now spins are of two types. The Earth spin is called the prograde spin. It is the same direction as Earth, and the retrograde spin is the Venus spin. It is opposite to the Earth spin. So for Earth and for other prograde objects, 1 upon tau equals 1 upon tau star minus 1 upon P. While for Venus, 1 upon tau equals 1 upon tau star plus 1 upon P. So let's take the example of Earth. For Earth, the P is 365.25 days and the tau, a solar day, is 1 day. So tau star is 0.99727 days equals 23 hours, 56 minutes and 4 seconds. Now, if Earth have been retrograde, then the tau star will have been even more than 1 minute. Sorry, 1 day. Now, a year in two ways. In a solar year, there are 365 days in a year, with 1 day being 24 hours long. While in a sidereal year, there are 366 days in a year, with each day being 23 hours, 56 minutes, and 4 seconds long. Think of it like a clock's hand. The minute hand completes a full circle, but the hour hand has also moved. so they don't realign at the same spot. So that's why the hand has to move somewhat more to actually align with the hour end after an hour. This is why the 23 hours 56 minutes become the 24 hours. So our familiar 24-hour day is not Earth's true rotation period. It's Earth's rotation period relative to the sun. Does anyone have any doubts? Okay. Now, is sun really periodic? We set our clocks by the sun, but does this, in the earlier periods, we have used sundials as our clocks, which is directly based upon the sun. But does the sun always cross your meridian exactly 24 hours after it did yesterday? No. The solar noon shifts by up to 16 minutes across the year. And there are two reasons for this. The reason one is the Earth's orbit. It is not a circle. In early July, it is an aphelion. It is the Earth is the farthest from the sun and it is moving slowish. So the sun moves slower across the sky. While in early July, which is a perihelion period, the Earth is the closest to the sun, moving fastest, and the sun moves faster across the sky. Now everybody just scan this QR code and there will be a Menti question. You can attempt that. Everyone, please scan it. I am only seeing 20 responses, but there are 31 people.
Can you switch back to the previous slide, please? The one before this.
Okay, can I switch back?
Yes, thank you.
Do you have any doubt, specific doubt?
No, no, I just want to know.
So as I was saying, in the winter solstice, the sun is away from the northern hemisphere while closer to the southern hemisphere. And that's why the southern hemisphere has summer season while the northern hemisphere has winter season. Similarly, for the summer solstice, there is a summer season in the northern hemisphere while winter season in the southern hemisphere. So in the month of December, Australia actually goes through the summer season while North America faces winter season. It depends upon the axial tail and not the distance of sun from the earth. Which brings us to the second reason. The sun wanders and clocks don't. Time is measured across the celestial equator via the right ascension, right? But the sun moves across the ecliptic, which is tilted 23.5 degrees to the equator, as Anisha may have told you. Near equinoxes, the sun's RA changes fastest, and near solstices, sun's RA changes slowest. So even if Earth's orbit were perfectly circular, solar noon would still drift because the sun's projection onto the equator is uneven. That's why the astronomers have introduced a mean sun concept. The real sun is always changing the positions in a year. So the mean sun is an imaginary point that moves along the celestial equator at perfectly constant speed, completing one full revolution in exactly one tropical year. Some differences between the real sun and mean sun are: the real sun moves along the ecliptic, but mean sun moves along equator. The speed of the real sun varies, while the speed of the mean sun is constant. The real sun gives true solar time, while the mean sun gives mean solar time. I'll get to the third point later. And the hour clock that we use in our daily life follows the mean sun, not the real one. The real sun is sometimes up to 16 minutes ahead or behind. Now the equation of time. Equation of time is the true solar time minus the mean solar time. During the early November, the maximum equation of time is plus 16 minutes, while the minimum is minus 14 minutes. The equation of time varies from minus 14 minutes to plus 16 minutes, and it becomes 0 4 times in the year. A sundial shows true solar time. Your clock shows mean solar time. The difference between them at any point in the year is the equation of time. Your sundial isn't wrong. It is just measuring as something different. Does anyone have any doubts? Did you get the Menti question? Okay. Now let's photograph the sun. Why? Just because. Same time, same place, same camera. Every single day for a year. What shape would the sun trace? Now, if the Earth were tilted and its orbit were perfectly circular, the sun would stay in one spot. That is the mean sun. But it does not. The tilt of the Earth and the orbit were the only two reasons that I explained earlier. And these makes a path difference. Something like this. The figure 8, and it's called an analemma. The upper lobe is from the May to August, and the lower lobe is from November to February. Just look at this. I'll explain it later. So why does it go up and down? This is due to the axial tilt of Earth. The north-south stretch of the analemma comes from the Earth's axial tilt. The vertical axis of the analemma is simply the sun's declination across the year. It ranges from plus 23.5 degrees to minus 23.5 degrees, which is exactly the Earth's axial tilt. Now, the previous analemma that I showed you, it is only for the northern hemisphere. In the southern hemisphere, this analemma flips and the whole shape becomes upside down. The upper lobe becomes bigger and the lower lobe smaller. Now, why does it go left and right? That's because of the equation of time. The equation of time is the east-west wobble of the analemma, and it is just a visualization. The east-west axis of the analemma is equation of time plotted spatially. The maximum wobble is approximately 16 minutes. That is approximately 4 degrees of the sky. And that's why we needed the mean sun. The real sun simply doesn't behave. Does anyone have any doubts in the LLM scene?
Can you again explain the last relation of equation of time with an LMA?
The equation of time is what forces the, suppose we are photographing the sun at exactly plus 12 a.m. Sorry, 12 p.m. in the afternoon. Then some time of the year it will be 16 minutes farther, while some time of the year it will be 14 minutes below. So that's why the sun is not at the same place horizontally in the whole year. It is fluctuating from here to there. And that's why the left and right comes. If we are photographing the mean sun, then it will just wobble from up to down and no left to right. But due to the equation of time, the wobbling happens in left to right motion.
Okay.
Did you get it?
The diagram of analemma that you showed, the points of so points on the analemma, they represent uh, the position of sun at the noon time. Am I right?
Yes. Yes.
Okay.
Okay, let's move forward. Now there are three clocks and none agree. Nature gave us three natural cycles to track time. The problem is they simply don't divide into each other. Now, one day is 24 hours. We are talking about the solar day. 1 month is 29.5 days. We are talking about a synodic month, which is the time between two successive moons, which is 29.5 days. And 1 year is 365.25 days, which is the tropical year, is the time from one vernal equinox to the next, i.e., when the sun collides, when the sun comes like one vernal equinox to the next. And every calendar in history has attempted to manage this mismatch. The big mismatch here is 1 year it becomes 12.37 months with this calculation. None have fully succeeded, even till now. 11 days every year. 12 full moon cycles fall short of a solar year by almost 11 days. 12 into 29.5 is 354 days, and 1 year is 365.25 days. The difference is 11.25 days. If we only follow the moon, the calendar drifts by 11 days every year. And in 16, yes, does anyone is having doubt?
No, no.
So follow only the moon and the calendar drifts by 11 days every year. So in 16 years, the summer month becomes the winter month. Now we can just follow the moon. Let's see what happens. If we ignore the sun and follow the moon and just start a new year after 12 months. Now moon phases are predictable. Any shepherd can track it. But summers start drifting into the winters. As I said earlier, Ramadan in the Islamic Hijri calendar is a purely lunar calendar, which moves through all four seasons over 33 years. Some years Ramadan falls in summer and some years in winter. Now, this is good for the religious observance, but this is very bad for agriculture purposes. Now, what if we just follow the sun? This is the other simple solution. Now, seasons are perfectly fixed, like summer will only come on July and winters on December. Agriculture will be very predictable, but the months have no relation with the moon. This is the Gregorian calendar. It is a purely solar calendar. Christmas always falls in winter in the northern hemisphere. Diwali doesn't because it follows the moon. Now, this works beautifully for agriculture, but not so much for the religious purposes. What if we want both? Track the moon for months and track the sun for years. We need to reconcile that 11-day gap every year. So now let's talk about a coincidence that is with this. 19 tropical years equals 6939.6 days and 235 synodic months equals 6939.7 days. So 19 years and 235 months are almost exactly equal. Now 19 into 12 is 228. And if we add 7 extra months, that will be 220. 235. So adding 7 extra months every 19 years will keep everything in sync. This is called the Metonic cycle. It was discovered by the Greek astronomer Meton in 432 BC. Now let's see how it was implemented. Have anyone seen this calendar in their homes or shops? Give a like. Yes, Sashwat, do you have any doubt?
No, no, sorry, it was by mistake.
Okay. Yes, Bhargavi, do you have any doubt? Okay. So you have all seen the Thakur Prasad calendar at home or in your local shop. Every single thing printed on it, the tithi, the nakshatra, the muhurat, comes directly from the astronomical system that we are about to discuss. The Indian lunisolar calendar. It doesn't just track the sun and moon, it tracks their relationship to each other, degree by degree. Nakshatra has 27 sectors of the ecliptic, each 13 degrees 20 minutes wide. The month is named after whichever nakshatra the full moon occupies. Tithi, the time for the moon to move 12 degrees ahead of the sun in celestial longitude. It is not fixed for 24 hours. It can be from 20 to 27 hours. You may have seen a few days in the lunisolar calendar to be repetitive. Like today is Tritiya and next day is Tritiya too. Elongation, the angular distance between the moon and the sun. A tithi equals 12 degrees of elongation. A full moon equals 180 degree, which means 15 tithis from new moon. And that's exactly what happens. There are 15 days in one whole lunar cycle. Look at that every nakshatra, tithi, elongation, everything constitutes of the angles between the sun and the moon, and not just them independently. Now, some days repeat, some disappear. Because a tithi lasts 20 to 27 hours, not exactly 24, sometimes a tithi and a sunrise don't align cleanly. There's this Adhika Tithi, where a Tithi spans two sunrises. Whereas Kshay Tithi, a Tithi starts after sunrise and ends before next sunrise. And that day name never appears, while Adhika Tithi appears twice. So if Tritiya starts at 5:28 a.m. and the sunrise is at 5:32 a.m. on day 1, and the next sunrise is at 5:31 a.m. on day 2, then Tritiya can span both sunrises if it is 25 hours long. So 2 consecutive days are both called Tritiya. The extra month. Even with Tithis keeping months in sync with the moon, the calendar still drifts from the solar year. The fix, add an extra month every 2 to 3 years. If the sun does not transit into a new zodiac sign Rashi during a lunar month, that month is declared as Adhik Masa. We are not getting into this detail because it's a long story, but just for a short note that this month currently is Adhika Masa and it will end in 3 to 4 days right now. Like currently Adhika Masa is going on. Example, if this happens before Chaitra, the extra month is called Adhika Chaitra and the real Chaitra follows immediately after as Nij Chaitra. This happens roughly 2 to 3 years, 7 times in 19 years because of the Metonic cycle. Adhika Masa is considered inauspicious is in Hindu tradition because there are no weddings and no new ventures in this month. Now, there's not an astronomical reason for this inauspiciousness. It's just a belief. Now, does anyone have any doubts? Yes, Bhargavi. Um, do you have any doubt, Bhargavi? You can unmute. Yes, Tarun. I think Bhargavi can speak. You can write in the chat and I'll answer your question in the WhatsApp group. Hello. I think we should move forward. Does anyone else have any doubts, or should I move forward? Let's move forward then. I think my mind isn't, I can't speak or chat. What? Wait a minute. There is audio on video. Guys, please chat in the WhatsApp group. I am checking it. Allow mic for attendees is on. Allow camera for attendees is on. I don't know. I have given the permission. Anisha, can you just check? if-
He asked a doubt like he didn't understand the Metonic cycle.
Okay, I'll explain it. And can you just check if why is anyone not able to unmute? Like I have given the
Okay, I'll
permission.
check that. Yeah, no,
So
I can
about
unmute. I think other people can.
I think I can also unmute myself. Can you hear me?
yes, I
It
don't
could
know
be
why
just
this
a
problem.
browser issue. It could
Okay.
be a browser issue actually.
Okay. So let's leave it. You guys can just text me on WhatsApp and let's go to the Metonic cycle first. So the Metonic cycle is the 19 years and the 235 months coincidence. First of the astronomer Meton discovered this coincidence that the 19 tropical years actually were equal to 6939.6 days and 235 synodic months were also equal to 6939.7 days. So he thought about that if we just add 7 extra months every 19 years, then everything will be in sync. So this cycle of 19 years where 7 extra months are added, this is called the Metonic cycle. This was a very brilliant solution discovered by Meton to reconcile that 11-day gap every year. Was it clear? Whoever has asked the hashtag. Okay. Did Vihang clear the Tritiya and Dvitiya doubt? Okay, I'll explain it. So about the Tritiya example, the Tritiya, it's like there's firstly, I don't know what was the first one. Purnima or something. No. Let's take Tritiya. So Tritiya and let's suppose today. Today is Tritiya. And today sunrise starts at 5:28 a.m. And tomorrow sunrise starts at 5:32 a.m. And okay, Tritiya starts at 5:28 a.m. and today's sunrise is at 5:32 a.m. So Tritiya covers today's sunrise. And next day the sunrise is at 5:31 a.m. and the Tritiya is about 25 hours long. So Tritiya itself will cover the 5:31 a.m. that is the next day's sunrise. So the Tritiya will just cover the whole span of both sunrises. So these two consecutive days are called Tritiya. It's not Dvitiya. Dvitiya just came before Tritiya. The days of the numbering of the days is not done like this. Like if it spans 2 days, then it's called Dvitiya. If it spans 3 days, it's called Tritiya. and no day can span 3 days. It's just not possible because 20 to 27 hours, you can't fit 3 sunrises in 27 hours. Did you got it, Tarun? Not really. Okay, how should I explain you? Like, I should explain it with the help of the calendar. Wait a minute. See here. In this calendar, one day is the first day. Let's suppose in this calendar, the first day is the second day is Dvitiya. I don't remember the name of the first day. The second day is Dvitiya. The third day is Tritiya. The fourth day is Chaturthi. And the fifth day is also Chaturthi because of the sunrise thing happening. And then the sixth day will be called Panchami. Seventh day will be called Shashti. The eighth day will be called Saptami. So this naming of Dvitiya, Tritiya, Chaturthi is based on just a normal cycle. It is actually Sanskrit. In Sanskrit, 2 is called Dvitiya, 3 is called Tritiya, 4th is called Chaturthi. And that's how the naming is done. And the Tritiya spanning over 2 days. We'll just name both of these days as Tritiya. 3 and 4 both will be called Tritiya and 5 will be called Chaturthi. Now, if there's any specific doubt that I can explain, then you may ask. Yes, Pratipada. Yes, remember. Pratipada. Pratipada, Dvitiya, Tritiya, Chaturthi. Pratipada, Dvitiya, Tritiya, Tritiya, Chaturthi, Panchami, Shashti, Saptami, Ashtami, Navami, Dashmi, Ekadashi, Dwadashi, Trayodashi, Chaturdashi, and was Purnima. Shall I move forward? Does anyone have anything else? Doubt? So let's move forward. Let's move forward to the history of Rome. When priests controlled time. Before Caesar, the Roman calendar was not an astronomical system. It was a political tool. Firstly, the old Roman calendar was there. It was 304 days, 10 months, only March to December, and winter had no days. Then there came the Republican calendar, 355 days and 12 months. The priest added an intercalary month every 2 years or didn't, depending on who was in power. Different kings came in power and they all had different calendars. Then came Caesar's Rome. When his calendar 3 months, the calendar was 3 months ahead of season and July was falling in spring. Now priests added and skipped months to extend friendly governments or shorten enemies' terms. The whole time was manipulated. No, 365 days. Caesar traveled to Egypt and saw a cleaner 365-day solar calendar and came back determined to fix Rome's mess forever. The fix was 365 days plus one leap year, one leap day every 4 years, equal to 365.25 days per year. Now, tropical year is not even exactly 365.25 days. That will be too good to be true. Tropical year is exactly 365.2422 days, while the Julian year was 365.2500 days. The error was merely 11 minutes 14 seconds per year. That was 1 day per 128 years. Small enough that nobody noticed for centuries, but it was there, quietly accumulating. Then Caesar was assassinated, and the priests got their hands on the leap year rule again. declaring a leap year every 3 years instead of 4 for the next 36 years because of the political issues. The 10 days that never existed. By 1582, Caesar's 11-minute error had accumulated to 10 full days. The vernal equinox had drifted from March 21 to March 11. The fixes. The immediate fix was October 4, 1582 was followed directly by October 15, 1582. 10 days simply vanished. And the permanent fix was century years are leap years only if divisible by 400. 1700, 1800, and 1900 are not leap years, while the year 2000 is a leap year. This reduced the error from 1 day per 128 years to 1 day per 3226 years. Now there's a still a error, and there's a proposed further fix that years divisible by 4000 are not leap years. This will move the accuracy to 1 day per 20,000 years. This is not yet implemented, and this is a problem for future astronomers to implement. Does anyone have any doubts in this Roman calendar part or any part overall? I'm seeing the WhatsApp chat. Okay, then that was all from us now.
One last thing.
Both.
So earlier, long ago, I studied, or I was actually told by somebody, that it was in the Gregorian calendar that we, introduced leap years for the masses.
The Gregorian calendar introduced leap years for the masses.
I mean, that's what I heard, because the first time I heard about the leap years being introduced in any calendar, it was the Gregorian calendar. This is the first time I'm hearing that somebody before the Gregorian calendar also used the leap years.
Okay. Gregorian calendar, I mean, the Romans actually adopted it from the Gregorian calendar. As you can see, I told that Caesar traveled to Egypt and came back with the fix. So Egypt was actually adopting the Gregorian calendar itself. That's how Caesar brought it to Rome. I was just talking about the Rome's politics here in the last section. I was not talking about the formation of the calendar or anything. The Gregorian calendar was formed very earlier, but in the Egypt, but like anywhere. But Caesar got the inspiration from Egypt and brought it to Rome. That's all. Okay.
Any
There's
doubts
another.
in coordinate systems? Yeah, sorry, continue.
Okay, there's a doubt in the chat that so you are saying we will still need to correct for some days in future years. Yes, the error is not fully solved yet. The error is still 1 day in 3226 years. And it can be even better if the 4000 year leap year part that I explained earlier. 1 minute. This one, the 20,000 years. If the years divisible by 4000 are not leap years, then the accuracy will move to 1 day per 20,000 years. But this is not yet to be implemented. This will be implemented in the upcoming future. And still there will be no error. There will be some error left. We cannot exactly cure this error. So are there any further doubts in my part or Anisha's part? That's the problem for the Martians now. Nice. Okay, go through the booklet once to get a better understanding, and don't forget to attempt the assignment. The assignment has been made more on a creative basis, and so try to understand it firstly, and how the calendar question especially, it was like I really liked that question, so attempt it wisely. And the deadline is 14th. I hope you all the best, and make sure to attend all the sessions. Attendance is compulsory. Okay. Anisha, do you? Okay, there's a question. You will be sharing the resources. Yes, I'll share everything in the MS Teams as well as the WhatsApp group. Don't worry. It will be there by like 6 or 7 p.m. today itself. Does anyone have anything else to say? Anisha, would you like to say something?
Yeah, go through the module once. There's a part on spherical geometry, which is very important to convert coordinates from one system to another. So yeah, go through the module once. But yeah, and the assignment will be out later today, and the deadline will be Sunday, end of day.
Yeah. And also go through the calendars part. There's a lot of history given. And if you enjoyed the calendars part in my slides, then you will also enjoy the module. So you can go through that too. Okay. If no one has any doubts further, then we can end this
Uh,
meet.
just one thing, if we have some further doubts, we can just ask in the chat, right?
Yes, the group is made for that itself. You can
Okay,
always ask in.
okay, that's great. Thank you.
Okay, then. Shall I end the meet? Anisha?
Yeah, I think we can end the meeting.
Okay, then. Thank you, everyone. That was a really nice session.